Hey everyone, it's Bradley Bush again with another algebra video. Today we are talking about finding all of the zeros of a polynomial. It's actually kind of a fun activity and it can be a little bit involved, so we're going to kind of break it down for you today. The to-do list, first thing is how to find all of the zeros of a polynomial, because there are many ways you can do it, and then we'll do two worked examples. And we have, as a bonus, we'll throw in some of the linear factorization theorem as we go in the second example. I'll also put the timestamps for each of these items in the video description, so if you want to skip ahead, you're welcome to. All right, so how do you find all of the zeros of a polynomial? And by the way, when we say all of the zeros, we really mean all of them. So you could have rational ones, you could have irrational ones, and you could have imaginary ones. So the irrational and the imaginary are often found using the quadratic formula. So if you have more than two roots, then sometimes you'll use all of these other ways to find all of the other roots that are rational and whittle it down to the ones that are kind of hard to find, and then we oftentimes will use the quadratic formula to find those remaining two roots, whether they're irrational, whether they're imaginary. But here are some ways you can find roots. And when I say roots, really roots are just x-intercepts. We should point that out because that's actually kind of important. You can call them roots, you can call them solutions, but really you're just finding x-intercepts. So when you find an x-intercept, all you do is set the function y, or f of x, however it may appear. You set equal to 0, and then you just solve the resulting equation for x. So you can factor this equation. If possible, you can complete the square if you've got a second degree polynomial or a parabola. You could use the quadratic formula if you have a parabola, or if you whittled the number of roots down to just 2, and you have 2 remaining. You could use a graphing tool, maybe perhaps like a handheld calculator or Desmos.com. You could also use synthetic division, and when we use synthetic division, we use it in conjunction with another tool like with graphing or with the rational zero theorem. We're going to use the rational zero theorem here today in our examples. That'll help us find all of the rational ones, and then we'll use the quadratic formula to find the others if they exist. Here's some helpful notes on roots and zeros of polynomials. The first one is, if you have a polynomial of degree n, that means n is the highest exponent. So say the largest exponent in your polynomial is 3, then you would have a polynomial of degree 3. So if you have a polynomial of degree n, then counting multiple roots separately, you will have exactly n roots or n solutions. So if we have a third degree polynomial, or a polynomial that has the highest exponent of as 3, then we know that we have at most 3, we will have exactly 3 roots. Not all of them may be real, but we'll have exactly 3 roots. Which, that's kind of cool. I mean, we know going into it how many we should be looking for. And if we happen to have imaginary roots, they always come in complex conjugate pairs. So a plus bi and a minus bi. So they always come in pairs of 2, conjugate pairs. So let's keep both of those in mind. All right, here's our first example. Find all the zeros of, and then it gives us a polynomial f, x cubed plus 2x squared minus 5x minus 6. So remember, this is a third degree polynomial because the highest power we see is 3. So we should know that we should be looking for 3 roots. They might not all be real. If they're imaginary, they'll come in pairs of 2. So we're going to use the rational root theorem to find all of the possible rational zeros, and then we'll use a graph to find out which of those possible rational zeros are actually the real ones, or they're actually the valid ones, the legitimate ones. So the rational root theorem tells us that if we take factors of the constant term, that's a sub 0 right here, and that's negative 6. And we take factors of the leading coefficient, which is 1 here, What are factors of -6? Well, it's kind of a lot, right? We have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Factors of the constant term are plus or minus 1. So the rational root theorem says that we can take the factors of the constant term and put them in the numerator here. Just going to copy those down, and we can take the factors of the leading coefficient and put them in the bottom. So when we have a fraction like this, it kind of looks messy, but we just take each of these separately and see what we get. And lucky for us, when we take each of these separately, the plus or minus 1 in the bottom cancels out. So really all we have is the plus or minus numbers that we have in the very top. So I'm going to copy those down. Wow. I'm not sure where that came from, but that wasn't what I wanted to do. So we have these options, plus or minus 1. So we've got 8 options. We have positive 1, negative 1, positive 2, negative 2, so on. So if we graphed this, we could easily see which ones were the valid ones. So we have negative 3. Where's negative 3? So that's this right here, right? And what about this one, negative 1? That's right here, negative 1. So that will be that one. And what's the last one? Last one is positive 2. Positive 2. There we go. Come around here. Awesome. Maybe I should stay consistent and put an arrow towards the actual root instead of the label. Awesome. So we have negative 3, negative 1, and positive 2. Those, when we graph it, that's what we see. So it looks like, according to our graph, that of all of these 8 options that we started out with, the only 3 that are actually valid would be negative 3, negative 1, and 2. So we can actually use synthetic division to test to see if these 3 x values are actually roots, right? Because if we do synthetic division, our remainder should be 0 if these are actually roots. So let's try testing all 3 of these. So let's test x equals negative 3. So we will bring the first number down, 1, and we get 1 here. 3 times negative 1 is negative 3. We add them and get negative 1. 3 times negative 1 is positive 3. And we add them and get negative 2. And negative 2 times negative 3 is positive 6. And we add them and we get 0, which is exactly what we wanted, right? We wanted a 0 remainder. We've confirmed that x equals negative 3 is indeed a root. We have confirmed that x equals negative 3 is a root because it has a 0 as a remainder when we did our synthetic division. So we can keep going and continue to test our roots. And a cool thing about synthetic division here is that we can actually take these numbers. We don't have to start over with our synthetic division. We can take the numbers that where we left off, and we can use them. So 1, negative 1, negative 2, and just keep going. So let's keep going. We have 1. We drop the 1 down. Negative 1 times 1 is positive 1. Negative 1. We add and we get negative 2. Negative 1 times negative 2 is positive 2. And we add those and get 0. Perfect. We just confirmed that x equals -1 is, in fact, a 0 because it has a 0 remainder when we did our division. So now let's keep going. We can take what's left over here and continue with our synthetic division. It's a little trick that you can use. Bring the first one down 1, 2 times 2 is, or 2 times 1 is 2, and you add them together and you get 0. Again, 0 remainder. We've now confirmed that all three of these are indeed zeros. So we have confirmed that x equals 2, x equals -1, and x equals -3 are actually zeros and roots of this polynomial. Super cool. All right, here's the second example. So in the last example, we had a third degree polynomial, and how many roots did we find? We found 3 roots. So here, the degree of this polynomial is 4, so we expect to find 4 roots. Again, we don't know how many will be imaginary, how many will be irrational, and how many will be rational. But let's start out with finding the rationals first, and then see what we have left over. And we will actually throw in some of the linear factorization theorem with this, because that's actually kind of cool. So let's start out by doing what we did before with finding the possible rational zeros. So again, we find the factors of the constant term. Oh man, that is a really big number, right? What are factors of 24? Eek. Whatever it is, it's big. There are a lot of them, right? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. I might have to move this over a little bit to give myself some more space. Plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. Oh wow, that was a lot of them, right? Hopefully we don't have to find or check all of those. So the next thing we do is we look at the leading coefficient, which thankfully is a very small number. Easy to work with. 1. What are factors of 1? Only plus or minus 1. Cool. So I can copy and paste these like we did in the previous example. There are a lot of them. And we have the plus or minus 1 on the bottom. So lucky for us, we can just copy and paste all of those. So how many of these do we have actually? 1, 2, 3, 4, 5, 6, 7, 8 times 2 is 16 possible options for rational roots. So of course we know not all of these are rational roots because we have 16 of them and we only have 4 roots total that we could have. So not all of these are going to be valid, but we know all of our valid rational roots are inside of this group because that's what the rational root theorem says. So let's look. When we graph it, oh wow, that's interesting. We graph it, look what happens. We have 2 right there. And the function comes down, touches the x-axis. Somebody didn't label their axis. What a terrible thing. Comes down, touches the x-axis, and then goes back up. So we know from our rules of algebra that if a function, a polynomial, comes down and touches the x-axis and goes back up, that means that it has a multiplicity of roots, or zeros, meaning we have repeating roots, and they repeat the number of, the multiplicity is an even number. So it's either 2 or 4, because we can't have more than 4 roots. because our degree is 4, and we can't ever have more roots than our degree of the polynomial, or the highest exponent of the polynomial. So because, so this tells us that 2 either repeats twice, and the other 2 are imaginary, or it repeats 4 times, and we don't have any imaginary. So how do we know? It's a really good question. How do you know how many times it repeats? Because you can't just stare at it and tell. Well, what did we do last time in our last example? We used synthetic division to find out if there was a 0 remainder. And if there was a 0 remainder, we knew that it was a root. So why don't we do that? Why don't we just keep testing 2's and see how many times we get 0 remainders? So let's try it. So we're going to test 2. And just for the sake of time, I've already done a lot of the work here. So we're going to test 2 the first time. So we know that it's going to have 1, 2. In fact, we know that it'll at least have 2 roots of 2, but we don't know if it'll have more than that. So here we go. The first 1 comes down, and then we have 2 times 1, which gives us 2, and we add, and we get 2. 2 and 0 is 2. 2 times 2 is 4. We add -6 and 4, and we get -2. 2 times -2 is -4. We add -8 and -4 gives us -12. And 2 times -2, 2 times -12 gives us, typo, -24. And we add and we get 0. So as we assumed and knew would happen, we verified algebraically that x equals 2 is indeed a root. So the linear factorization, so here's the bonus that I told you we were going to throw in. The linear factorization theorem says that anytime we know that we have a root, we know that we can factor out an x minus that root from our polynomial. So I just did it. X minus 2, so our root was 2, so x minus the root would be x minus 2, is going to be a factor of the polynomial. And what's left, how did I get the rest of this stuff here? Where did that come from? Well, if you notice, we started out with the x to the 4th for this one. The next one is x to the 3rd. The next one is x squared, x, and then the constant term. So when we drop down one level in our synthetic division, we lose an exponent. So this here now was x cubed, this was x squared, this was x, this is the constant term. So those numbers in the bottom here, those are just the coefficients, which I just wrote down here. So that's actually pretty cool. So I know that x minus 2 is a factor, and I can pull it out. And so I don't even have to factor. I'm not even factoring, doing it the hard way. I just know that x minus 2 can be pulled out as a factor, and then what's left over, the stuff that's left over, I just take from the coefficients from my synthetic division. So that's kind of slick. So we know x minus 2, or x equals 2 is a root one time. And we know it's going to happen again, right? Because we know we at least have 2. So let's just get the algebra over with here. So we do the same trick we did last time, where we take our answer and we drop it down, and we'll start working from there. So let's do that. So 2 times 1 is 2. We add 2 and 2 and get 4. 2 times 4 is 8. Add -2 and 8 and get 6. 2 and 6 gives 12, and we add and we get 0. So awesome. We knew that was going to happen, right? So this is now, it used to be an x cubed, now this is an x squared, this is an x, this is the constant term. So that's what's left over right there. And notice we have an x minus, another x minus 2. So the blue x minus 2 is the first one we verified. The second x minus 2, the purple one, is the one we just verified now. And what's left over, we see from our coefficients, Right there. Fantastic. Now, what we have left is a quadratic. Interesting. So that's what we have left is a quadratic. So we verified that x equals 2 times. And so we know that multiplicity, this root has multiplicity of at least 2. But does it have 4? Or do we have 2 imaginary roots? Well, the only way to find out, I guess we could just throw it in the quadratic formula right now. What's left? We could throw that in the quadratic formula and come out with the other 2 roots. But we could also verify quickly. So let's verify by synthetic division again, because if we get a remainder that's 0, we know that we'll end up having 4 2's instead of just 2. So let's see, the 1 comes down, 2 times 1 is 2, 4 and 2 added together give us 6, 2 times 6 is 12, we add them together, we get 18. That's not 0. So we have just confirmed that we only have 2 2's as roots. So the other 2 have to be, the other 2 roots that remain must be imaginary. And how are we going to find those? Well, again, we have the first root and the factor for that root. We have the second root and the factor for that root. So we will just use the quadratic formula to find the 2 remaining roots that are going to be imaginary. So our quadratic formula is here, just in case you forgot it. Our 8, b, and c are 1, 4, and 6. Those are the coefficients in the quadratic. And then we just plug them into the formula. The b is green here. Here and here is the b. And we have an a and a c, and then an a in the bottom. As we condense here, 4 squared is 16, and we have negative 24 here. 16 minus 24 is negative 8. The square root of negative 8 is an imaginary number, and I've computed it here. You can take the I out, the negative 1 out as an I, and then the square root of 8 can be simplified into square root of 2 and 2 out front. So we have 2i times the square root of 2. Which we put down here. We've got the negative 4 out front and the 2 in the bottom. So we've got 2's in each of the parts of our problem. We have a 2 in the negative 4, we've got a 2 here, and we've got a 2 in the bottom. So if we cut a 2 out of each of those, we factor a 2 out and cancel, then as you can see, this 2's gone, this 2's gone, and we have a 1 here and a 1 here. And this negative 4 becomes a negative 2. So our answer then is negative 2 plus or minus I root 2. And again, there are 2 of them. There's the positive one and there's the negative one. So here on the left is the negative 2 plus I root 2. And then we have negative 2 minus I root 2. So we have found all 4 of the roots. 2 of them were real, 2 of them were imaginary. But let's finish with the linear factorization theorem, because I think it's kind of cool. So again, we had the root x equals 2, the first one. Here's the second one. And these 2, we ended up getting 2 imaginary roots. We ended up getting negative 2 plus I root 2 and negative 2 minus I root 2. So we're going to plug those in because the linear factorization theorem says we can just plug a root in, x minus the root, and that gives us the factor. And there's the second one. And then when we distribute, it's kind of important, right? Distribute the negative through each, changes the sign everywhere, and we get our result. They're the 2 new ones with the sign changes after we distributed the sign in. So our function, which was x to the 4th minus 6x squared minus 8x plus 24, that function, that polynomial, can be factored into this. x minus 2 times x minus 2 times x plus 2 minus I root 2 times x plus 2 plus I root 2. And we found all 4 roots. It's x equals 2, which occurred twice. We had a multiplicity of 2, right? And we had the 2 imaginary roots here. Hope this was helpful. There's a lot of information here. You might need to rewatch it a couple times, but there's a lot of really, really good information. Hope it was helpful. If it was, like the video, follow the channel, subscribe to the channel, and have a good day.